All right, Pete, I think it's time. Ready for you whenever you're ready.
All right. Thanks, Dan. Appreciate you setting this webinar up along with Michael. And thank you, everybody out there. Um, some of you may have heard me talking about our flood forecasting product. I've been talking about it for quite a while, probably 4 or 5 years, and it has been evolving over that time. And we have some new features that we recently added that allow us to not only forecast inland, but to forecast along the coast. And that's what I want to talk about today. And so I'm going to shut my video off just to save a little bandwidth. And yeah, so the topic is flood forecasting in coastal transition zones at the street level. And we do that through FloodWise, our new flood forecasting product. So the topics that I want to go over today, I'll do a little bit of an introduction so that everybody's clear on what we're talking about relative to real-time flood forecasting. And then I'll spend a little bit of time talking about compound flooding in coastal transition zones. That's where the fresh water meets the salt water. And then I'll show you how FloodWise works, how the system works, and then we'll go over a couple of case studies, and then we'll kind of close it up at the end. So on the introduction, real-time flood forecasting at the street level, what we mean by that is real-time is what's happening right now. We don't care about what happened an hour ago or 5 hours ago. We're concerned more with what's going on right at this moment. And then flood forecasting is what is likely to happen in the next few days. We're not looking 50 years down the road or the impact of climate change or anything like that. We're trying to figure out what's going to happen tomorrow, the next day, or the next 3 days or so. And then at the street level, we can pinpoint these forecasts down to specific streets, specific houses, buildings, and other critical infrastructure. And this is all about how we can recover, mitigate. It should be prepare, mitigate, recover. Prepare, we can be more specific about emergency management coordination. Mitigate, sometimes there are things that we can do in advance to actually alter the outcome of a flood that's about to come. And then recover, we can recover much faster if we know where the problems are going to be. And so if we could know this 1 to 3 days in advance, precisely where the flooding will occur and how long it will last, we've kind of asked that question. And we can anticipate road closures, we can pinpoint evacuations, we can move vehicles out of harm's way, we can be much smarter about how we deploy sandbags and temporary flood walls. We can reduce or even eliminate wastewater overflows. We can optimize water control structures. We can lower lake levels ahead of time to create more storage, or we can plan recovery efforts much sooner. So compound flooding in coastal transition zones, what are we talking about there? A lot of you probably have heard about compound flooding, mostly in coastal areas. We could have other types of compound flooding, but what I want to focus on is in the coastal area. So if we look at this sketch here on the right side of it, this is where we have the rainfall and riverine flooding. And if the coast, if there wasn't any surge there and we had just normal tides, the flood profile would drop down toward the coast. But if we had storm surge and high tides like king tides on the coastal part, that could push inland. And if the inland flooding wasn't a problem, that might be limited to here. But when you combine those two, the inland flooding and the storm surge and tide, you get this transition zone, which is where we have the compound flooding. It's the effect of both the storm surge and the rainfall induced flooding. And how wide that or long that transition zone is depends on an almost infinite number of factors. Depends on antecedent conditions up in the upland portion. It depends on all the storm surge considerations like wind direction, wind speed, pressure, all sorts of things affect the where the water levels in the ocean will be, and that combination, and I'll demonstrate that in just a minute, can vary. It can be a short transition zone, or it can be a much longer transition zone. So here's an example of where we have a coastal transition zone. This is in southern Lee County and portions of Collier County. And in particular, what we were looking at here is the city of Bonita Springs, which is down here. This has a large headwater wetland system. It's called the Corkscrew Swamp in this area, and the flow patterns can change depending on the distribution of rainfall across this. If we have higher intensity down in this area and lower intensity up here, that might affect the flow pattern in one way. But if that was to reverse, then the flow patterns can change completely. And we can pop off over here, we can pop off down here. But a lot of that water will run through the Imperial River out to the Estero Bay right here through the city of Bonita Springs. So in this model, we use 2D overland flow in these areas where we're not certain which way the water is going to flow. We don't have very well-defined flow patterns. But west of I-75, this is highly urbanized areas. We use traditional 1D H&H modeling there. So this is the Imperial River through the city of Bonita Springs. And the blue shaded area is how it was inundated during Hurricane Irma. And this was the result here. Well, quite a bit of flooding, and it lasted a pretty long time, several weeks. So let's compare Hurricane Irma to Hurricane Ian. Hurricane Irma across the Keys and then approached land kind of in the Port Charlotte area and Fort Myers area. But it kind of skirted the coast, then it went up through the center of the state and then worked its way up into the northern areas. The heaviest rainfall with Hurricane Irma was on the right side of the storm, whereas on the left side of the storm, the intensity wasn't quite as bad. Hurricane Ian was quite different. The storm approached almost perpendicular to the coast, and this was just almost in the same place as Irma, but you can see Irma kind of ran parallel to the coast, whereas Hurricane Ian made a right turn and just created a very high surge in the Fort Myers Beach area. But all the rainfall, or not all of it, but the heaviest rainfall fell on the left side along basically the I-4 corridor. So we had the heavy rainfall there, not as heavy on the right side of the storm. And this is the NOAA tide station at Fort Myers. The one at Naples blew out during Hurricane Irma, and they have since replaced that, but they moved it to a different location. So we wanted to look at Fort Myers. And so the red line is Hurricane Ian, and the blue line is Hurricane Irma. And we actually had a negative surge with Hurricane Irma before it reversed direction and then went positive, whereas Ian was primarily positive surge up to about 7.5 feet NAVD. So the peak surge with Hurricane Irma was much less than the peak surge with Hurricane Ian. And this is Hurricane Ian Hurricane Irma along the Imperial River. we had about a 4 foot, and these are all elevations of NAVD 88. So we had a surge of about 4 feet along Bonita Beach. And then in Estero Bay, it was about elevation 4. And then these higher elevations are not due to storm surge, but they were due to heavy rainfall out in the headwater wetland system to the east. Okay, and here's I-75 here. These are all based on high water marks surveyed by the USGS after the storm. So the transition zone from the coastal portion to the inland portion was relatively short and relatively short-lived. The highest water levels were due to the heavy rainfalls out to the east of I-75. Hurricane Ian, which was much different, the storm surge along Bonita Beach was between 11.5 and 12.5 NAVD. It was about 11 feet at the mouth of the Imperial River, and then that surge pushed up a good ways in upstream in the river, so we had a much longer transition zone. But the water level just east of I-75 was a couple of feet lower than it was for Hurricane Irma. Let me go back to Irma. Irma was 13 here. Ian was 11. And at 11, there is some flooding, but nowhere near as bad as Irma was from the rainfall. So we had some short-lived flooding due to storm surge, but not very much due to rainfall. And Hurricane Irma was just the opposite. Very little storm surge flooding, mostly rainfall-induced flooding. So the question is, how can we account for this? How can we account for both the storm surge and all the variables associated with the rainfall-induced flooding, and basically do compound flooding in real time rather than a probabilistic type of compound flooding? And that's what we want to talk about. So flood-wise, how does it work? So flood-wise, you might think of that as the brains of this system. Flood-wise is bringing in all sorts of data from different places. It's doing some pre-processing. It's archiving data, and then we have Stormwise, which is the old ICPR4. Stormwise out there is like the muscle, and it's doing all the hydraulic and hydrology calculations. So we can have multiple instances of Stormwise. For example, we can have a system set up for Bonita Springs. We can have one in Orange County. We can have one up in Mecklenburg County in North Carolina, one out in Texas. So all of these run independent of the other ones, but they all request their data through Floodwise, and Floodwise determines whether there's a coastal hookup, whether we're using USGS stream gauges. We can also incorporate St. Johns River Water Management District live data, and then we're pulling in rainfall and ET forcing data. And the rainfall and ET data are pulled in on a continental scale on a 1 kilometer grid. And so Stormwise says, okay, I don't need the entire continental United States. I only need a smaller subset of that. Here's the subset that I need. Floodwise will extract it from the overall set and send that out to Stormwise. Floodwise will say, okay, this instance of Stormwise needs 12 different hookup points for the coastal forecast system. It needs 12 stream gauges, USGS stream gauges, and it sends that data out to Stormwise. And then Stormwise does its calculations, sends its results back to Floodwise. Floodwise then posts it in an outward-facing dashboard system. So Stormwise, those of you who aren't familiar with it, like I said, this is formerly ICPR4. We can do strictly 1D surface water we can do integrated 1D and 2D surface water, or we can do integrated 1D and 2D surface water with 2D groundwater. In any combination of these, we can do inside Stormwise. So we can build some pretty sophisticated H&H models and then run them in the Floodwise system. On the coastal end of things, this is something that we're pretty excited about. We got this hooked up several months ago. NOAA has a product out there where they're calculating real-time water levels across the globe. Yes, you heard me right, across the globe. And they're serving that data up, and we're grabbing it. So every 6 hours they update it, and they include in addition to the real-time 6 hours that have happened, they are forecasting out 180 hours. And so these are the computational points. These blue dots here are the computational points for the NOAA coastal product. And so what we do is we look at those points shown in blue here, and then the red points are part of the Stormwise model, and those are the hookup points or the coastal nesting points. And so what we do is we say, okay, at this red dot, maybe use the NOAA product here, results from this, and apply it to this point, and so on. This point, we might grab that NOAA point and use that as a boundary condition. That becomes a time stage relationship for the Stormwise modeling system. And if we look at that in the dashboard and we click on one of these pins, which is one of the coastal nesting points, you can see the blue are the real-time simulations. And then in this case, we have 3 different forecasts, one on April 5th, 6th, and 7th. And when I took this screenshot, this vertical line here is what's happening at the moment. And then everything to the right of that is a forecast. So we were forecasting in this case around April 11th, higher than usual tide. And then in the dashboard, some of these points here start lighting up. They turn orange and red if they're at risk of flooding. Orange is a flood warning. Red is a flood alert. Okay, so let's go over a case study here. Manatee County. This is a system that's up and running as we speak. We combined 3 different ICPR models together: Bowleys Creek, Pierce Drain, and Whitaker Bayou. Whitaker Bayou is in Sarasota County, and these 2 are in Manatee County, and they all share water depending on the current conditions. We have drainage into Sarasota Bay. This is Sarasota Bay down here. And then we also have a connection over in the Braden River, which drains into the Manatee River, which is tidal. Okay, so we took these 3 individual models, merged them together into a single model. We have all the normal Stormwise / ICPR stuff in there: open channels, culverts, bridges, catchment areas, and so on. So it's a regular ICPR / Stormwise model, except we set it to run in real time. We add risk points to the system. We call these flood risk points. These can be locations along streets. It can be houses, lift stations, law enforcement facilities, police stations, fire stations, hospital, medical, nursing, schools, anything that our clients want. We can drop points in to keep track of whether they're at flood risk or not. These are not part of the computational framework. Instead, what we do is form a relationship between these points and the computational network. and we can determine if any of these points are going to be at risk of flooding. Red, you might think of that as deep flooding. You probably couldn't drive a passenger car through that. If it's on a house, that means it's probably in the house. The orange points are shallow street flooding or yard flooding. And then green is no flooding. And so I like to say green is good, red is bad. Kind of an easy way to look at it on the dashboard system. In this case, we set up 3 different coastal nesting points, or 3 hookup points with the NOAA coastal forecast system. This is where Whitaker Bayou comes into Sarasota Bay. This is where Boldy's Creek comes into Sarasota Bay. And this is where the Pierce Drain, Gap Creek goes into the Braden River and then hooks up to the coastal system here. And the way we do this is, let's say that this point, this red point right here, is the end of the Stormwise model, the end of the ICPR model. In there, we put in some variables in the comment field, and we tell it to get the NOAA data from this point. We tell it to go out into the bay because we know that point will always be wet, where these other ones can be wet or dry. So we say use the water levels, the forecasted water levels out in the bay here, and apply them to the Stormwise node at this point. And then that becomes a boundary condition for the rest of the model upstream. And when you look at it on the dashboard, you'll see a pin there, and you click on that pin, and the blue is the tidal fluctuations that have already occurred. And then these other colors are different forecasts for different days, and the red is the most recent forecast, and that's what is about to happen. We took this combined model and we calibrated it, and we looked at NextRad, using NextRad rainfall data, and then we looked at it using the FloodWise rainfall data. We used to call it the RTFF system, real-time flood forecasting system, and then compared them to the observed data at, I think we looked at 5 different stream gauges, and for 2 different storms, Hurricane Ian and Tropical Storm Eta. And then we looked at the county, Manatee County wanted us to look at about 5 different other storms and different kinds of combinations of storm surge and rainfall. And so we provided them with that information. So this is all part of the model setup, calibration, verification. Once that's done, then we go operational, and it runs 24/7, 365 days a year. And we checked it. We're able to go back in time and kind of hindcast some past events and see how well the system did during those past events. So this past April 11th, there was a kind of a king tide event, and we had forecasted 3 days out exactly what the observed elevation turned out to be. 2 days out, we were very close to that. 1 day out, we were a little bit higher. But in all 3 cases, up to 3 days out, we were very close to what actually ended up happening. Then December 17th last year, there was another pretty big wind-driven surge event. And so we compared that at this gauge, and keep in mind that's upstream quite a bit. So at this point, we have both effects of rainfall and storm surge. And again, we're bracketing the final observed elevation pretty closely, 3 days out, 2 days out, 1 day out. And then this is going back the end of last August, Hurricane Idalia passed through the area, and these forecasts bracketed once again the observed elevation. And that was upstream. You can see some of these points, these wrist points, are changing color. That means they've hit the warning elevation. But most of these are still green, so they were still in pretty good shape for Hurricane Idalia. So the system is operational for 3 years. It runs 24/7. We put it on our computational server in Huntsville, Alabama, at a data center. The dashboard is accessible from any web browser. And then we actually went through training on this as Hurricane Idalia passed through the area. So that was kind of exciting. And then since then, the county asked us to add all the coastal fringe areas to the system. And these are areas that are immediately adjacent and directly connected to saltwater bodies. Okay, so we're not really doing rainfall-induced flooding in these areas. We're just looking at how a storm surge event, how that would affect things, what streets it would flood. This is Holmes Beach or Anna Maria Island, and this was the April 11th event of this year. And the observed elevation was 2.82 at Port Manatee, which is kind of a little bit north and east of here. And this was a 3-day early warning. And we had a photograph of that area. We were predicting the flooding along the street here, and that's what was observed during that event. This is the December 17th event from last year. The surge was actually higher than the April event. And you can see the red here are the deeper flooding, the orange is shallow flooding, and the green is up above the flooding. And so we were predicting as early as 3 days out the specific areas that were going to go underwater. And then Hurricane Idalia was worse still, and so this was the 2-day early warning on Idalia. Notice a lot of red area, a lot of deeper flooding along the roadways. And then here's the entire fringe area that we've added to the system. And again, red is bad. The orange is kind of shallow flooding, but still water standing in the streets. We have Port Manatee is up here to the north. This is Anna Maria Island. I think this is Longboat Key here, the Manatee River, and then the Braden River here. And again, we're predicting this out several days in advance. We can also list out all of those risk points for each of the forecasts that are getting lit up. In other words, where we're hitting alert and warning elevations. Another case study, Cedar Key. This was after Hurricane Idalia. I say Hurricanes Idalia and Franklin. Franklin is out here in the Atlantic. Idalia was running up the coast of Florida, and this was the path of it, and it crossed up and it made landfall in the Big Bend area. And the right side of the storm is where the highest surge was, which is where Cedar Key was located. And this is just a photograph during the storm, August 30th. Pretty good size surge event. So we just kind of set up a model of this system, and we dropped in the risk points, and then all these pins are places where we connected to the NOAA forecast system. And we were getting a 48-hour warning with this system down to each of these points. And we were within 3 inches of the observed level at the Cedar Key tide station. And then zooming in closer, this is an evacuation route. We were predicting that to flood a couple of days in advance, and then all of these other roadways internal to Cedar Key. And then we just zoom in some more. And so, if you were here high and dry and you waited too long to evacuate, you would not be able to get out of this system in a normal passenger car. And then the last one I want to show you is this is Cape Coral, and this is Fort Myers, and this is Hurricane Ian. And here's an aerial photograph of an intersection. And this is a combination of both storm surge and rainfall induced flooding. And again, the red is bad, green is good. So we had some deep flooding all around the perimeter. And this is the Caloosahatchee River here. And this is Sanibel Island, Fort Myers Beach over here, just devastated from the storm surge. And you can see how that drops off as you move inland. These are surveyed USGS high water marks. But the impact is just devastating. And we did show this to a lot of people. We had this up at a number of conferences and kind of a large TV screen. And we had a number of people come up who said that they had houses in this area, and we kind of asked them about it. Did your house flood? No. Was your yard underwater? Yeah, the yard was underwater, but the house was okay. And sure enough, we'd have an orange point there. And then they said a few blocks south of them, water was in the houses. And so we zoomed in on that on the map, and were able to show them where we had predicted the flooding, and they affirmed that indeed did happen. So just to summarize, this is an automated system. It runs on our servers in Huntsville, Alabama, and it runs 24/7, 365. We fully integrate the coastal and the inland systems. We're doing compound flooding in real time for the coastal transition zones. So we're building all of that into it, antecedent conditions in the upland areas, combined with the wind-driven lunar tides. All of that's built into it, so we can pick up flooding when it's not raining, like king tides. We can pick up flooding from wind-driven events, non-tropical systems, just wind-driven, and we can also pick up tropical storm systems. We place flood risk points along the streets and other critical infrastructure, and we key off of those, identifying which of those risk points are at risk of flooding at any point in time. We can forecast at the street level up to a week out. That's as far out as the NOAA forecast goes, a week out. And we work off a very intuitive dashboard system, so you don't have to be an expert modeler. You just have to interact with this through the dashboard system. And then we can also do what-if scenarios from the dashboard system. What if it rains more or less than is forecast? What if we turn a pump on sooner, leave it on longer? All of that can be evaluated from the dashboard. And that's it. So let me, so we can open it up now to questions. My contact information, by the way, is right here. So if you want to send me any follow-up questions after this, please feel free.
Awesome, Pete. We've got some questions in the chat right now. I'll start off with the first one is this real-time NOAA data just limited to coastal zones globally or inland locations also?
The NOAA system is it's an AdCirc model, if you're not familiar with that, but but the AdCirc model is for both out in the open ocean, but into estuaries. They do have a fair amount of detail inside the estuary systems. They do not do rainfall runoff computations at all. They're just doing the storm surge and tide levels. We do not include wave runup in this system. That's something we may add in the future, but right now we're not doing wave runup. So it's strictly storm surge and tides. The Stormwise model does all of the inland rainfall runoff processes, and think of the NOAA data as um, a time variant, excuse me, time stage boundary condition.
All right. So the next question here is, what are the reporting intervals for the tidal and rainfall forecast data used for FloodWise?
We output data every hour.
Just clear his throat.
Yeah, we output data every hour.
And the next question is, can this dashboard platform send data to other third-party applications or make data available for third-party applications to use?
I'll let you know.
It would require some customization to do that. You can, from the dashboard, download data. Like if you pull up a chart, you can export that data to a CSV file. But right now, we're not sharing the data with any other applications. We have had some discussions about that and could do it, but it would require what the application is and how we go about sharing that data. All within the realm of possibilities, yes.
And what kind of operations can be included in the what-if scenarios?
Right now, we can do pump stations. You can change on-off settings for individual pumps in a pump station, and you can do what-if scenarios on the rainfall. You can, if the forecast said there was 6 inches, or even the forecast might say 6 to 10 inches, you could put in 10 inches and run that as an alternative and evaluate the impact of that. Also, you can alter the pump operations from the dashboard. We will likely, we have another way to change gate operations. We will probably incorporate that into the dashboard in the not too distant future.
What causes a NOAA point location to go dry? It's our next question.
Well, they have actually pushed their computational mesh up into the upland areas in anticipation of a storm surge. Let's say there was a 12-foot storm surge that would push inland. And so their computational mesh goes inland, and those nodes, those NOAA nodes, are almost always dry. But if there was a very large storm surge event, then they would become wet. So in our case, Stormwise is modeling all of the inland impacts. So we don't really need all of NOAA's inland nodes. We do a more rigorous assessment of those relative to the rainfall runoff process. So anyways, if one of their nodes goes dry, they flag it with, I don't know, something like negative 100 meters or negative 1,000 meters or something like that. And so rather than grab that, we're always trying to assure that we get a wet node.
And here we go. Do you use IoT sensors to get the data? And can it create simulation for the future, also based on the fact we are developing a new category for hurricanes?
Um, we are not using any sensors at all. We are right now, we can grab USGS stream gauge data, stream stage data. We can grab live St. Johns River stream stage data. And the way we have it set up, we can plug in other types of gauges. So if there are other ones out there and other sensors, we could add that if a client wants us to. And we are not doing any type of machine learning at this point, any type of AI, trying to forecast into the future.
Potentially, how far upstream in miles can storm surge influence Florida's rivers? For example, can the Green Swamp be influenced by coastal conditions?
That would take a pretty big tsunami to get to the Green Swamp, but the St. Johns River is a really good example where surge could affect it all the way to like probably close to Lake George, which is near Palatka. So that can go inland quite a ways. The impact varies. Like I said, it varies depending on the particular system. I showed you the Imperial River, and that was maybe 3 or 4 miles inland with Hurricane Ian, whereas Hurricane Irma was only maybe a mile inland. But yeah, the storm surge can have a big effect on big river systems and estuary systems. So with like the lower St. Johns River, where it comes out at Jacksonville, Noah's model would have a bunch of points in there, and we would tap into those points rather than try to model that estuary system ourselves.
And the last question in the chat is: you mentioned the modeling running real time for 3 years. What happens after 3 years?
Well, if the client wants to extend it, then we extend it. That's just that particular one. Manatee County, our contract with them goes for 3 years. If they decide they want to extend it, all they have to do is tell us, and then we extend it for as long as they want. We can also do updates to the system. Like if they want to update the model, maybe there were some changes over that 3-year period, we could build in any new modifications and then keep it going beyond that point.
All right, Pete, those are all the questions that have come in. If anybody has any lingering ones, drop them in the chat really fast, or you can always email Pete. You see his contact information there at the bottom. Do you have any closing remarks, Pete?
Just thank you again, everybody. We're really excited about this technology, the storm surge. We've been testing it quite a bit, and we've been very pleased with how accurate it has been. So we're pretty excited about that. Also, NOAA is always making adjustments to their model to include sea level rise and things like that as the years go on. The product that they're using is also used by the National Hurricane Center. So we're real pleased with it so far. So again, thank you, everybody. Really appreciate you taking time out of your day.
Thank you, Pete. Thanks, everybody. Bye now.